Swayam Prabha. Digital India. Educated India.
Okay, good morning. Today's lecture is on another cycloaddition reaction, that is 4 plus 3 cycloaddition reaction, and it is very similar to one we talked about in the last class. If you recall, in the last class we talked about 4 plus 2 cycloaddition reactions, and we had given examples on the 4 plus 2 cycloaddition reactions where the furan and other molecules undergo 4 plus 2 cycloaddition. In addition, we have seen some of the Bogar kind of chemistry where you have these diagenes, tetragenes, those molecules also participate as diene components. And then we have also talked about these azadyl reactions. One of these reactions is popularly known as Povarov reactions, which is basically involves amines, or sometimes we call amino-Diels-Alder reactions. Today we talk about a very similar reactions, although it is 4 plus 3. If you recall, these 4 and 3, all these numbers refers to the number of the atom forming the rings. Okay, so it basically they are the numbers of the each reacting components, and to compare with what we will be talking about today, let us say this is the standard protocol for Diels-Alder reactions or 4 plus 2 cycloaddition reactions, and then normally what we require is electron withdrawing group at one component. So, that was the standard one. Now, today's one is a very similar one, but only thing what you will find that the dienophile does not have an electron withdrawing group. Instead, you will have a carbocation, that is it. So, I mean, what you can think about, actually many of you probably know that the Diels-Alder reactions can be carried out like say in the presence of a double bond here with like say a ketal, for example. If you take a ketal here, although it is not an electron withdrawing group, but many of you know mechanistically this carbon can form a nice carbocation in the presence of a Lewis acid. So, essentially it is a double bond and a carbocation. Very similar to that, if you think about a reacting component where you have olefin and then you have a double bond. So, that means this carbocation is as if is serving this purpose of electron withdrawing group. So, the reactions should have undergone Diels-Alder kind of reactions, but instead what you see, the result is little different. Result is little different. It is a 7 membered ring. That means all the 3 atoms of the allyl carbocation, all the allyl carbon, this is the basically allyl carbocation would undergo reactions. So, that is the reason why it is known as the 4 plus 3 cycloaddition reactions. And obviously, on your left hand side, that means diene side, you do not have much choice. So, the diene has to be, or dienes have to be electron rich, and the dienophile is now allyl cation. But again this simple version is not really known, and if you look at the reactions here, it is not the cycloheptene, it has to be a carbocation here to balance the charge, right. This is basically the formal 4+3 cycloaddition reactions. And what are and then there are, but this simple version is not really known, but what is known is equivalent to that kind of things. There is one more kind of reactions probably I think which is more popular, and suppose you have something like this, then a carbocation here, this allylic carbocation actually has to be stabilized by choice of different substituents. Okay, this is very important. On the left hand side diene part we do not have much options, but what you will see as we proceed along the class, we will see that most often these reactions are tuned by placing different substituent here and there, okay, and most often it is the heteroatoms, and the commonest one is oxygen here, and that is called oxygen minus here, and this is very well known in the literature, is known as oxyallyl cation. So, one can even in fact call 4+3 cycloaddition reactions of oxyallyl cations. So, that means, and if you look at this, this is nothing, this is equivalent to something like this. Then as if you have a carbonyl compound and one side you have a carbocation, the other side you have a negative ion. So, this is primarily the basic reacting units for all these 4+3 cycloaddition reactions. Then we will have different examples, different methods of making how they are used, and then also some of these applications, the applications, and it does not have to be necessarily this kind of things, but the precursor could be something like an epoxide or amino substituted epoxide, all kinds of things. We will proceed, we will give you more examples. Let us take a simple but yet tougher examples. Here this was published in 2012, and well, the page number is 4528. What is there? Here you have a benzofuran in this case, and you see this mechanistically is very simple. Mechanistically very simple is benzofuran, all of you can write, and then you have an alcoholic OH group and a methyl group here. Then other reacting component is a cyclohexene, and then you have double bond here and this. So, all of you can guess what it is. This cyclohexene and vinylic double bond that would form the diene part, then you do not have a dienophile. In this case you do not have formal dienophile, but in the presence of CSA, what is known as camphor sulfonic acid, which is basically mild organic acid, and then this solvent, of course you have to use a polar solvent because you are using a sulfonic acid. So, polar solvent, and the temperature is somewhere between 35 degree to 40 degree centigrade. So, normally if you did not know the 4+3 cycloaddition reaction, we would have expected no reactions in this case, right. At best, in the presence of camphor sulfonic acid, this alcohol would undergo dehydration to form the corresponding diene systems, but the result in this case is remarkably good, in the sense I will tell you why it is remarkable, the reaction result is remarkable. You get a 7-membered ring, and then the cyclohexane get fused, and this double bond, and then this methyl group here, okay. So, mechanically you do not have to go through these 4+3 cycloaddition reactions. What you can do, you can think about as if this is forming the carbocation here, this carbocation here, right, this carbocation here. So, that means you have a pi system, you have a carbocation here, and then what? Then this middle one, the allylic systems will have an oxygen here, and all of us know oxygen will in presence of the double bond, adjacent double bond, it polarizes the electrons toward these beta positions. So, that means essentially this is equivalent to what you can see this oxygen here double bond, and this is negative charge, and then you will have a positive charge here, then this methyl group here. So, and this is equivalent to a carbonyl group, and then adjacent to it you have a plus and you have minus. So, all these reactions, if you have this middle one is oxygen, it is equivalent to a carbonyl compound. So, and then 1, 2, 3, that means 3 atom dipole, you can say 3 atom dipole, you can say it is not truly the dipole, but in this case it is tripole, you can say. And then of course, you have this cyclohexadiene part, and that would undergo reactions as you can see from here, double bond would participate, this would migrate, and then negative charge would this and this negative charge would combine with this other end, eventually giving the 6-7 membered ring. Why so is it important? Probably many of you know this reaction is a very important reaction. There are 2 reasons. Partly one of the major reasons is that there are very few reactions in which you can make a 7 membered ring systems. Do you know any standard protocol? There is no standard protocol. One of these ways to make 7 membered ring system is Dickmann reaction, Dickmann condensation reaction, that is one of these ways, but all of us also know this is not kinetically favorable, thermodynamically also not favorable, because they are unstable reactions. Unstable. Any other method, do you know any other method for straight away making a 7 membered ring system? Absolutely, 7 membered ring systems, there are not many. So, so that is the reason why this reaction is very useful, this reaction, and there are plenty of examples, there are plenty of examples and plenty of variations. And in this case, now if you treat this with paratoluene sulfonic acid, number 1, and then treat this with boron tribromide. So, what you get? You get same sorry. So, I better write the 6 membered first, then furan ring system, you have double bond this and 7 member ring, then you have a 6 member ring, 2 methyl group here, and what else you like to see? Something else, what else? Okay, this is this molecule is known as frondosine. Frondosine B is an enzyme inhibitor, and then there is a methyl group here. So, this methyl group here now is stereochemistry is all defined, and you may have to you have to recognize also as you go proceed along, it is not an heterocyclic chemistry, it is just an aliphatic chemistry now. Okay, in the okay, what do you expect with paratoluene sulfonic acid? Any guess? Quick. Paratoluene sulfonic acid would induce dehydration. What else? In this case, it actually isomerizes the double bond. Double bond comes into the conjugation with the furan ring system. So, the double bond is moved. Then probably many of you know boron tribromide. Boron tribromide is a famous reagent for demethylation. So, that means if you have let us say phenyl methyl ether, how do you generate phenol from phenyl methyl ether? Quick, classical method, phenyl methyl ether. How do you convert phenyl methyl ether corresponding phenol? Na? No. No, you have to know quadratic acid and all this. This is a very standard reaction, BSc reaction. Harjic method. Have you heard of Harjic method? Harjic method, HI. HI. So, if you just treat with HI, it is simple undergo. This is just even high school chemistry. Okay. Problem there, you require high temperature. In this case, the reaction can be carried out at minus 78 degree centigrade. So, you get this. So, okay. And what else? What are the other things we learned from here? That means, simple allylic cation is sufficient to activate an allylic activate the substrate to participate in 4+3 cycloaddition. Not only that, what you can see here, although you have a furan here, that furan double bond can participate in these 4+3 cycloaddition reactions. So, before or we have learned that furan undergoes Diels-Alder reactions as a diene component, but here the furan double bond is an acceptor component, means a dienophile kind of component. Okay. And let us so that, but it is not forming a heterocycle though, it is forming a carbocycle, 7 membered carbocycle ring system. Let us look at some other examples where you will see that heterocycles are being formed, and it is a kind of the substrate here, in this case again a ketone, right, and alpha prime. What you do here, you treat this with zinc copper couple. It could be simple also copper bronze. This is another. So, basically reducing agent, and treat this with now it is a furan. So, if you add furan, so what you will find, I mean you will find oxyallylic cation. So, essentially this is again a kind of Diels-Alder kind of reactions, or you can say 4+3 cycloaddition reaction, and these and methyl group here and this. So, it is a bicyclic compound, and now it is a truly heterocyclic molecule, it is a truly heterocyclic molecule. What are the functions? How does it proceed? You can simply this one you can think of, all of us know this zinc undergoes oxidative additions in between these halogen and the carbon bond. So, you will have bromine here, and then this undergoes this can undergo 1,3 shift of zinc. So, result would be oxygen as zinc here and the bromine here, and then you have this. Now, also all of us know this oxygen zinc means basically oxyanion. So, it is equivalent to oxyanion here, and then you have a bromine which is equivalent to now. So, you can see now, so you have an oxyanion now, oxyanion. So, and it is called then under these reaction conditions, if you have a polar solvent, so you are likely to get a cation of this kind, and this is now this is oxygen minus, and this is double bond, and so then this electron polarizes towards the cation here, and then the negative charge goes to this oxygen, the double bond moves. So, eventually you get to this sort of molecule. So, this is again a 7 membered ring. Now, in this case with an oxygen, because you started with a heterocycle, that is furan, and this has been recently been used for again a synthesis of a natural product called salini-ketal A, which is nothing but it is heavily oxygen substituted natural product. So, what does it tell you? This example has many things to be learned. Number one, that alpha from dibromo compounds can be an oxyallyl cation precursor. Number two, that zinc can be used, zinc copper can be used, and then it is restricted to this dienophile which is diene, which is furan. There are other examples. For example, there are other ways to make this oxyallylic cation. The methods that is commonly used is something very uncommon, and it is presumed that this use of iron carbonyl gives this carbon bromine bond little more higher covalent character. Okay. So, that is why the reaction is quite facile. Now, if you react this with di-iron nonacarbonyl and the reaction temperature is very little less 30 degree centigrade, and if you treat this with furan and E, in this case E stands for ester, right. E stands for ester. So, once again, so nonacarbonyl is a very safe compound, though it is a liquid, it is commercially available, and if you photolyze it becomes iron pentacarbonyl, that is also a liquid, and it is basically serve the purpose of zinc, because it undergoes iron nonacarbonyl means it is iron plus carbon monoxide. So, it is basically iron 0, right, and so it undergoes insertion between carbon and bromine bond like zinc. So, that takes care of, and then this iron also activates this carbon bromine bond, that means take away this bromine away to produce carbocation here, and the reaction product in this case. So, that means you will have a ketone here, that means basically all these reactions is equivalent, all these reactions are equivalent to a reactions of the acetone at alpha position and alpha prime positions as a plus and minus, that is it. And so, furan here, the double bond now moves, and these furan ends are connected to these acetone ends alpha primes, and in this case this is something you have to sit down that actually this phenyl part or the alpha positions of the phenyl gets the positive character and the other part gets the negative character. So, this one is produced in 90% and other one is 10%, other one means this other residue isomer, and which is again is a furan, then the ester part is on the right. So, between the two, the difference is that the ester is one case it is ester is the on this phenyl side, other the other side. Okay. Now, but what I did not tell you in the first example is there are other things here that you have to be little worried about the stereochemistry. By virtue of phenyl and ethyl being on the same site and in the vicinity. So, one can just quickly say that if this is phenyl is alpha, then ester is beta because of this simple steric region, and in this case also it is this is alpha and this is beta. So, that is not a problem, but in most other cases you get the mixture of the compounds, Okay. That means you will have alpha, that means see this method, for example, in the previous case these methyl groups can be alpha to this oxygen, beta to the oxygen. So, similarly this one, that means, and then both the alpha both beta, all kinds of permutation combinations would be possible for these. That is the drawback of this 4 plus 3 cycloaddition reactions. In most cases they produce mixture of, unlike Diels-Alder reactions which are very stereoselective and in many cases very stereospecific, but in this case the reactions are not well defined with respect to the stereochemistry. Okay. So, result is that you get mixtures, but there are cases you get just single isomer simply because of the steric regions, what does it tell you? You get a mixture of stereoisomer. What does it mean? It is not a truly a pericyclic reactions, number 1. Number 2, that I mean this method or these reactions could be stepwise. See, when this, that means when there is no defined stereochemistry of the product, one can just simply conclude the reaction is not a very stereospecific reaction. Okay. So, in fact, truly these reactions are not very stereospecific, and then Let us look at other reactions, just other examples here. That means, in this case you have produced these oxygen heterocycles. Similarly, if you begin with once again with a bromide here and this bromide, then treat this with a pyrrole moiety and then copper. Normally copper bronze is used and the sodium iodide. So, sodium iodide, what you will find so basically again you get a 7 membered ring, and this in this case you have nitrogen and double bond, just like furan the reaction would take place, and both the methyl group is cis in this case with this nitrogen carbon bond is beta, that means this all trans to each other. These other possibilities could be simply again 7 membered ring, this carbonyl and this nitrogen, make it a beta here, nitrogen double bond, this methyl group, fine. So, what will expect, that means this is beta, carbon nitrogen bond beta, this methyl group also is beta. Okay. Now, I mean anybody can guess which one would be the major product. The trans one would be the major product. In fact, this is formed in 76% yield and this is formed 13% yield. So, this is just a case of, now this is just a case of nitrogen heterocycle. That means, what it means, that the pyrrole also can participate in these 4+3 cycloaddition reactions. Now, let us look at one more example where you will have unlike the previous examples, you will have a just alpha bromo ketone and then furan. Now, whether is it possible or not, this reaction. So, that means now you have to, whether first of all you have to do a feasibility test whether this reaction would occur or not. At least one thing we know about the diene part, we know that the diene is electron rich, that is not a problem at all. We do not have many options in the diene, either furan, pyrrole now, and in the previous example we have seen diene system, even simple butadiene, vinyl cyclohexene. So, that means we do not have much options, it has to be electron rich diene. And then we have now a precursor, in principle it could be an oxyallyl cation, right, but you have to choose the right reaction conditions. What is the reaction conditions could be? So, to pull out the bromine, the standard protocol is guess, to pull out the bromine from its reaction mixture to form a carbocation. See, normally formation of a carbocation adjacent to a carbonyl group is little tough. So, how do you do? So, you have to have a halophilic reagent, and what is the halophilic reagent? Silver. So, then in this example people have used silver tetrafluoroborate, fine. So, that takes care of this, that means that would pull out this. Then at the same time you have to form a anion here. So, how do you do? Just use a base, in this case triethylamine, that is enough, triethylamine, and then solvent, because you are using an inorganic compound silver tetrafluoride. So, you have to use a polar solvent. So, what polar solvent is used? Methanol, ethanol? No, you cannot use, simply because methanol, ethanol are sufficiently nucleophilic. If you take chloroacetone, alpha chloroacetone, put it in ethanol, after one day will come, you will see it undergoes solvolysis to form the methoxy acetone. Okay. So, that means they are sufficiently nucleophilic. So, what you can do, you can use this ethanol analog, a trifluoroethanol. and the difference between the just simple ethanol and trifluoroethanol is that this is less nucleophilic. So, less nucleophilic and the reaction proceeds to give once again this portion is acetone cyclohexenone portion, let us say, and so this is cyclohexanone portion, this other portion, this one is a furan portion. So, you get a nice architecture of an organic molecule. You can see here this is a tricyclic molecule can be made with very simple methods, that means alpha bromo acetones cyclohexanone is easy to make, and then of course furans are done. Now, similar reactions has been performed with again just a monochloro. So far we had discussed about this dibromo acetones etc. Now, you see that single bromine is sufficient to produce this oxyallyl cation here. Let us look at one more example. This is now it is a macrocycle now, it is a macrocycle and macrocycle with a ketone and then with a halogen at the alpha position here, and there are tricks where you can make this. Now, you have a substituent containing this furan ring system, and so once again basically the purpose is to engage the furan unit in the reactions with this alpha chloro unit, alpha chloro acetone unit in a 4+3 cycloaddition reactions. So, you can think about the previous reactions, right. You can think about the previous reaction conditions, that means you can use silver tetrafluoroborate, triethylamine etc. This is sufficient, but exactly it is difficult to say why that has not been used, but in this case there is a trick has been used, and this trick the trick here is lithium perchlorate, okay. Lithium perchlorate in ether, lithium perchlorate in ether, and of course the triethylamine. So, why suddenly lithium perchlorate? Normally it is actually 5 molar lithium perchlorate. Any idea? So, no halophilic reagent now. Base is there to form the carbon ion at the alpha position, other side of this carbonyl group, and the lithium perchlorate is to again to pull out this chlorine here. Okay. This lithium perchlorate actually was long back used by a pretty unknown scientist as a polar solvent. That means ether is a solvent, perfectly all right, but if you put little bit of lithium perchlorate, that means to the extent of 5 molar, actually the saturated solution of lithium perchlorate in ether is a 5 molar solution, it becomes very polar solvent. The solvent becomes very polar. So, once you have a polar solvent, that means carbon chlorine bond undergoes sorbolysis, means carbocation formation is facilitated, and eventually. So, what you will find again if you sit down, you will see that there is an intramolecular cycloaddition taking place, and so furan is now that means this unit is reacting here, and this this end, and this end is reacting to this. So, eventually you will get to this sort of molecule, and then you have by virtue of this geometry, you have this is beta and this is alpha, then you have this carbocycle, this other this that means you have these 3 here, right. So, 3 1 2 3 4 5 6 7. So, basically CH2 and this should be 7, CH2 7. So, you will have now a macrocycle produced, and then you can do all kinds of things, here. Okay. So, from dibromo to monobromo, then to monochloro. Now, let us see then basically you have to go to this Peter Sykes. How many ways you can produce carbocation? How many of you can recall? There are, I mean, almost 10 different methods one can make. How do you make carbocation? Just summarize. So, that is what people would do. Okay. So long we have removed a chlorine from this, that means an heteroatom. So, a substrate and a heteroatom, okay. And a heteroatom could be many. You can have nitrogen, you can have sulfur, you can have oxygen and all kinds of things here, okay. And that is what we will see. And in the next few examples we will see that sulfur, oxygen, all okay, nitrogen maybe depending on the situation. For example, if you have amine group and treat with nitrous acid, so it automatically release this nitrogen. So you have right, and then there are some certain tricks. There are certain tricks probably you do not know. There is a group called sulfone, SO2, pH, etc. The sulfone also is a nice living group in the presence of acid. That is not known. Most of us know that sulfone is an activating group to produce a carbon ion. If you have a CH adjacent to sulfone, it forms a carbon ion in the presence of strong base. But at the same time, if you have a sulfone in presence of Lewis acid and aluminum chloride, etc., it can form also carbocation. So, we will see one of these examples there with sulfur. For example, this substrate is again a variation of that, means intermolecular reactions. In this case, the substrate would look like this. That means a minimum requirement is a double bond, that is for sure, and you have to have an allylic substituent. In this case, is a sulfone and then toluene group, and in this particular example you have a cyclohexane unit, then you have 3 different carbons, then you have again a furan unit, and obviously and this one is ethyl now. So, once we write this, you can make out, I guess, which one is a allylic cation portion, which one this portion. So, that means basically what you have to do, your attention should be focused on the double bond. So, double bond, once you identify the double bond, you recognize which one. So, the allylic position is this and this, there is nothing here on this side, this, and you have this diene portion, inbuilt diene portion. So, it would be an intermolecular reaction, and now is to know the reaction conditions. So, you have to form the carbocation first, and ion formation is very easy. So, in this case the carbocation that is being formed, the sulfone is particularly reactive towards titanium tetrachloride, then diethyl aluminum chloride, means one single chlorine, dimethyl aluminum chloride, those sort of compounds. And in this example, it has been used this is titanium tetrachloride. Mechanistically, what you will see that this should undergo coordination with lithium. Actually, coordination takes place at the oxygen end. So, what you will find, this becomes the carbocation, and now this is ethyl here, and now obviously all of us know that in this case this anion is not required, because oxygen is sufficiently nucleophilic to polarize the electrons towards the ring system. So, ring system. So, the product would be again a 5 member ring, because you have 3 carbon, then you have furan, and then this is the ketone here, and then cyclohexane part, and there is, I missed one point here, there was an ethyl group here. In this case, this ethyl group would be resulting in this bridgehead, and by virtue of the steric effect, again once again this carbon oxygen bond is beta and you have the double bond. Okay. So, with this kind of success, then there are other variations of the sulfur substituents or sulfur substituents. Let me just give you the example and try to see whether anybody can make out. This is somewhat like to a problem for you. See here what I write here a double bond first, right. Once again a oxygen the middle one, and then you have now it is a different group, it is not a sulfone, the sulfoxide. Then you have 3 carbon and a furan unit again. So, that means furan is pretty is a popular diene for this kind of molecule, and in this case. So, difference is that this allylic position is having a substituent like known as what is the name of the functional group? Sulfoxide, and so that means sulfone would not work, and it is triplet triptylic anhydride and then 2,6 lutidine. What is it? 2,6 lutidine, and the solvent is methylene chloride. See here, you do not have any harsh conditions for the reaction, just very it is a kind of room temperature kind of thing. Okay. So, what do you see? Now, you have to basically you have recognized the substrate. Now, you have to see the reagent. 2,6 lutidine is basically pyridine derivative, 2 and 6 position 2,6 dimethyl pyridine. Okay. So, it is a hindered kind of a base, and triptylic anhydride all of you know, trifluoroacetic anhydride. And so, what do you expect? Or this reaction in this case again a very similar reaction, intramolecular you have 1, 2, 3 and through 4, 5. So, it is a 5 member, right, because this end would react, this end would react, this end would react, this end would react, right. So, that means if you count from here 1, 2, 3, 4, 5. So, it is a 5 membered ring, and then you will have this furan part and the other part will have again the connections here, and as usual in analogy the previous example you have this here, and there is a methyl substituent. So, methyl substituent now is alpha here, then it has to be beta here. Okay. But what else? What you will see here, this is something quite interesting. You will see now not a sulfoxide, what is it? SPH, sulphide, okay. And in this example you get a single isomer. Out of many possible isomers you get only just a single isomer. Once again it is an outcome of these steric effects and the reactivities, all these things. Okay. It is very difficult to explain. I mean, people have tried to explain these selectivities in with calculations etc., but they are not really manageable. Okay. But so you have but mostly it is a steric effect, and because you are forming a bicyclic compound, tricyclic compound. So, this ring strain all other things would be involved to define the stereochemistry of these rings junctures. Okay. So, but once again there is a trick though, new trick to produce carbocation. What is this carbocation? It is a carbocation is something like this. It is a system like this. If you draw the resonance structure, so it will be this. So, this means say now carbocation adjacent to SPH, and how do you make it? And by now Mona Lisa should have known, right. In your lab this reaction is done. What is this? some say Palmera rearrangement, some say Pumera rearrangement, and it is a Pumera rearrangement. Pumera rearrangement is nothing but it is a let us say if you begin with let us say pH, let us say sulfoxide and a CH3 up here, and just any acid, either Lewis acid or Bronsted acid, whatever the acid you use, just take an acid basically. Even simple iodine also sometimes works. What do you see? Let us say we begin with let us say the commonest one, let us say paratoluene sulfonic acid for example, paratoluene sulfonic acid. What is expected here is oxygen gets protonated. So, you get a sulfonium ion, or then now what do you see this one. So, there is a now loss of water. So, if you give the loss of water, what you will find? So, this should be CH, the previous example, the pH here, pH here. So, if you lose water, it will eventually it forms the sulfonium ion kind of this thing, sulfonium ion kind of these things. And then this of course, if you have nucleophile in the system, for example, let us say you have let us say sodium acetate for example, let us say sodium acetate. So, what do you expect? You will expect a pH, then C and hydrogen here S and pH. So, then if you just let us say use alkali. So, what you can guess? What you will guess? It will give you benzaldehyde. That means, starting from oh sorry, I think I made a mistake somewhere. I made a mistake somewhere. I will need a phenyl group here, right? You need a phenyl group here. So, it should be a phenyl group up here, then only you can get this, right. So, it should be a phenyl group, and so eventually that means if a phenyl sulfoxide can give you the benzaldehyde. This is a very useful reaction. There are very useful reactions to form a new carbon-carbon bond, and the product here of course, I think I should not miss this, there is a double bond here in the product. So, this is essentially an example where you can do some now just look at just one more very similar example. That means basically what we are trying to see, we have to have an allylic systems. In the middle carbon we will have an oxygen that which will form oxygen ion, and then this the adjacent carbon should have a group that would form a carbocation. So, sulfone and sulfoxide previously halogens, this thing that thing. Okay. Now, just we will see an application of this sort of reactions in the synthesis of natural products. This is a big molecule I will be writing here, just have patience to see. This is known as cortistatin A, the molecule. This is very recently it has been isolated, and the structure wise it looks like a kind of sort of a pseudo steroid. It is not exactly a steroid, but what you will see it is just meant for 4+3 cycloaddition reactions, because you have a 7 membered ring system, and also what you will see you have oxygen here, exactly what you want from a 4+3 cycloaddition reactions. Okay. And then there are so many other things here, OH group, then here another OH, then this NME group, then like a steroid, the last ring is a 5 membered ring. So, and there is this angular methyl group and this hydrogen here, and then in addition to that there is something here. So, it is a heterocyclic class. So, you have to have a heterocyclic nucleus, right, and in this case it is an isoquinoline nucleus, okay, and this has a beta position. Now, what do you right. So, there are two actually heterocyclic unit, one is the isoquinol unit and other is this furan ring system embedded in a 7 membered ring. Now, how can you okay, how can you make this? Okay, this was first attempted. This was first attempted with a target to make this only the steroid part, that means the part that is and they did a model study where they could accommodate OH here and then 7 membered ring and then 6 membered ring with double bond, the ketone, and then there is a 5 membered ring, right, and this angular dimethyl. This was this preliminary target and then this furan ring part. Okay. Now, what do you do? To start with, you have actually what you have to do, you have to do a sort of model study. So, what should be the model study? Model, that means you have to choose the right substrate. That means first of all you have to concentrate this part, that means you have to have a cyclohexane, you have to have a cycloheptane, this furan ring and a OH group. That means you have to create an OH group up here at the beta position. So, if you very closely look at, just look at the structure here, that means at one end you should have a furan part, right, that furan part, then you have to have how many carbons? You have to have 1, 2, 3, 4, that means 1, 2, 3 and one more, right, one more 1, 2, 3 and then you will have to have oxygen there, right, 1, 2, 3 you skip, the fourth one will have an oxygen. So, fourth one will have an oxygen which will have this like this structure. Then you will have a carbon, you will have then again a carbon here, then this carbonyl and then this, right, and then of course, the other things should be there, and let us say I put R here. So, you have to fill in the blank here. So, what sort of group should we require? That means to bring in this sort of backbone, that means basically what I am trying to say, we are just cutting down this complexity of this molecule, making it a simpler substrate, and we have identified that this portion should come from a furan and then this other part, right. So, all of us know this oxygen normally is oxygen minus or an oxy ether. So, okay, so we will maybe we can get it from this ketone here and let us say oxygen, so oxygen here, and in this case it is TES. TES is triethyl silyl group and R, okay, and then this this one is not having anything, right. So, but the other position will have an OH group and then you have 1, 2, 3 and then the furan, right, 1, 2, 3 and this is the furan part. So, you have to produce a carbocation basically here, that is right. So, how do you produce? You all know the answer. So, how do you produce a carbocation? That is the trick. So far we had only just given the examples, and now in this case you have to produce a carbocation. Once again Jenny March or Peter Sykes go to the chapter of carbocation. How to produce carbocation? Actually you can produce carbocation from any organic material, be it a carbon hydrogen molecule with, for example, even hydrocarbon also can be reacted with superacid to produce carbocation through hydride transfer. Okay. So, similarly, but the commonest one we have to look for the first the commonest one. So, we have removed the halogens etc., right, sulfone, sulfoxide, nitrogen we have not talked about. So, in this case let us say diazonium we have not talked about. Okay. What else? Alcohol, plain alcohol, if you have diol, let us say, if you have, let us say, in this case if you have an OH group you can think about, but you cannot think about, see if you have two OH groups then you will have competitions, right. Competitions you can expect a what sort of reaction you expect. If you have two OH groups you are side by side, if you are trying to pinacol rearrangement. So, that means you have to do a little bit of manipulations to skip the pinacol rearrangement. So, what you have to do, form epoxide. That means, what you have to do, you have to have an epoxide, you have to have an epoxide up here, that is it. So, if you have an epoxide here, all of us know, under the influence of acid, in this case it is again the acid here is TES and triplet, in this case acid triplet. Okay. So, and this is the reactions and that has been used, then okay, if you are interested I will give you the reference, I will give you the reference. This is taken from 2011 and chemical communication and page number 3416. Okay, those who are especially organic chemists, though you study this is a very interesting reaction, So, that means you see here, I mean if you just see here rightly matches with the target molecule. Then there are other molecules very similarly has been made, very similarly, that is not a heterocyclic molecule, but they have used intramolecular 4+3 cycloaddition reaction to produce a very useful molecule, though very useful molecule. If you can make a synthesis of this molecule simpler, you will be rich overnight, very rich. Anybody knows this name of this molecule? It is a colchicine. What is colchicine? Colchicine, okay. Just I will write, I will briefly write 6 member, then you have a 7 member, and then you have another 7 member ring system, here. Okay. This is aromatic, this is aromatic, and this is non-aromatic, and you have a nitrogen. If you just basically type in Google, you will find colchicine, nice structure. It has two stereo center. One is the chiral center itself, one is the axial chirality. That means basically you have 4 possibilities. The molecule is has been approved in 2009 as a drug for acute gout. Sagar, did you understand what is the meaning of gout? Okay, I know, that is why I asked you. What about Madhavan? No, you have Vasudevan. Right, pain in joints and all these things. In Bangla bole bath. Okay, and this is a very severe, no, believe me or not, at least people like me or like elderly people as me, will have the severe problems. Sometimes it is so acute, people just cry, and it is a very old molecule. It was isolated in 1800 something from a small flowery plant. Okay, then the people have tried to develop synthesis of this method. I mean, and there are about some 10-15 different methods how to make, but they are all of them are economically lousy, means not feasible. So, if you can make a good synthesis in 10